Hi everyone, I'm Julian. Today I'm going to talk about a framework for processing large graphs in shared memory parallel machines. This is joint work with people at CMU as well as people that I'm working with here at Berkeley. So many of you know that graphs appear in a variety of different domains. You can use them to represent social networks, the web. They also appear in many scientific applications, and these graphs can be very large. They can contain up to billions of vertices and edges, and therefore we need an efficient, scalable, and simple way to analyze these graphs to derive useful information from their structure. This was what motivated us to develop this graph processing framework, which we call Ligra. At a very high level, Ligra contains two very simple functions, an EdgeMap and a Vertex Map function. An EdgeMap is used to map some computation over a subset of edges in the graph in parallel, and a Vertex Map is used to do the same thing, but over a subset of vertices in parallel. I'll go into more detail about how these functions work later on in this talk. But at a high level, we show that just using these two simple functions, it's very natural to express a broad class of graph algorithms ranging from simple algorithms like breadth-first search to more complicated algorithms like local graph clustering and K-core decomposition. And in this talk, I'll also show you that the codes written using Ligra are very simple and concise. They perform well relative to hand-tuned implementations of the same application, and they also perform well relative to other graph processing systems at the time that we developed Ligra, which was a couple years ago. And finally, we show that we can use these codes to process some of the largest publicly available graphs out there on just a single shared memory machine. So of course, there are many other graph processing systems out there, so I've listed just a couple of them here. I can't list all of them because they won't fit on this slide. There's like a new one that comes out every week now. But at a high level, our system, Ligra, differs from these existing systems in that Ligra takes advantage of the frontier-based nature of many graph traversal algorithms, where the active set of vertices and edges is dynamically changing throughout the course of the execution, and it's often very small compared to the size of the entire graph. And most of these existing systems would not take advantage of this. They would actually process the entire graph even if only a small number of vertices and edges are active. Okay, so I want to introduce this simple problem, breadth-first search, or BFS, and use this to illustrate how Ligra works. So the definition of this problem is that we want to compute a breadth-first search tree rooted at some source vertex R, which is an input to the problem, and containing all the vertices reachable from R. So this might seem like just a problem you would see in the algorithms textbook, but it actually also has many applications in the real world. For example, it's used in the Graph 500 benchmark, which is a benchmark used to measure some of the performance of the most powerful computers in the world. It's also used as a subroutine in applications like betweenness centrality and eccentricity estimation. So as a result, there's been a lot of research on trying to develop a fast parallel implementation of breadth-first search. So I'll describe a very simple, this is a traditional breadth-first search algorithm. This is a parallel algorithm. So how it works is on each iteration, we maintain an active set of vertices. Initially, this active set would contain just the source vertex, so maybe this red vertex in the center, if you can see it. And then on every iteration, we're going to explore all of the outgoing neighbors of the active set of vertices, mark all of the neighbors that haven't been explored yet as explored, and place them onto the next active set of vertices. So in the first iteration, we'll explore all of the neighbors of the source, place them onto the active set. In the next iteration, we'll explore the neighbors of the neighbors that haven't been visited, or the neighbors that, or the vertices that are 2 hops away from the source, and then we go 3 hops away, and we keep continuing this until all the vertices have been processed, or all of them have been explored. So each iteration of this process that I just described can be processed in parallel, so you can parallelize over the vertices in the active set as well as their outgoing edges. However, you still have to wait for each iteration to finish before you proceed with the next iteration. Otherwise, the BFS tree you generate might not be a correct BFS tree. A parallel implementation of breadth-first search has to deal with race conditions because you could have multiple vertices on the same active set trying to visit the same neighbor, and you have to figure out who actually gets to mark that neighbor as visited. Parallel implementations also have to deal with load balancing because the amount of work on each iteration is changing throughout the course of the algorithm. And in fact, there have been many research papers written on how to develop efficient parallel breadth-first search algorithms. So what we did was we took a step back and we looked at what this breadth-first search algorithm was doing at a higher level. So at a high level on each iteration, it consists of 3 steps. So first, it's operating on a subset of vertices. This is the set of active vertices that I showed earlier. Then it's mapping some computation over a subset of edges in parallel. So for BFS, this subset of edges would be the outgoing edges of the active vertices. And the computation that we map basically is we just say that we're going to explore the unexplored neighbor. We're going to mark the neighbor as explored. Finally, it returns a new subset of vertices that we can use on the next iteration as we continue doing our breadth-first search. So breadth-first search just repeatedly applies these 3 steps until convergence. But actually, this is not just limited to BFS. Many graph traversal algorithms do this. They follow these 3 high-level steps. Some of them also have a 4th step of mapping some computation over a subset of vertices in parallel. This is used to update local information associated with the vertices. So BFS doesn't do this, but something like PageRank would, as you'll see later. So we built the Liger abstraction to capture these types of computations that follow these 3 or 4 high-level steps that I've shown on this slide. So we have a data structure called vertex subset, which is used to represent an arbitrary subset of vertices in the graph. We have an EdgeMap function, which maps some application-specific computation over a subset of edges associated with a vertex subset in parallel. And then it also returns a new subset of vertices, again represented as a vertex subset, and you can use this in future computations. We have a Vertex Map function, which maps some application-specific function over a subset of vertices in parallel. And finally, since this is a graph processing system, we have a graph data structure just to represent the graph itself. So Ligra encourages the programmer to think using these flat data parallel operators EdgeMap and Vertex Map, and we argue that it's actually pretty natural to express a broad class of graph traversal algorithms using these 2 flat data parallel operators. And it also enables us to do some optimizations that I'll talk about later. So Ligra is developed for shared memory machines. So we use Silk Plus to get parallelism. The code also compiles with OpenMP. And we have 2 optimizations implemented underneath the abstraction. This is the hybrid traversal scheme as well as graph compression. So I'll talk about what the hybrid traversal scheme is in a couple slides, and the graph compression stuff you can ask me offline. So here's how you would implement a BFS in Ligra. So we initialize an array of parents. So this is set to all -1s. So -1 means that the vertex has not yet been explored. At the end of the algorithm, what we want is for each vertex to have its parent entry that says who its parent is in the BFS tree. Okay, so now let's go to this BFS procedure down here. The first thing we do is we set the parent's entry of the source vertex R to itself. This is a special case. And then we place the initial vertex onto this frontier, represented as a vertex subset. Now we're going to repeatedly apply this EdgeMap function and assign the result to the frontier variable until the size of the frontier becomes empty. Okay, so what does this EdgeMap function do? It takes as input the graph G, this frontier, which is a vertex subset, and then 2 application-specific functions, update and cond. So to illustrate how this works, let's do a simple example here. So let's say our frontier contained these 4 vertices in this red box, and then all of the vertices shaded blue have already been explored in the BFS, and the unshaded vertices have not yet been explored. The first thing EdgeMap is going to do, it's going to apply this cond function to all of the outgoing neighbors of the frontier vertices. The cond function for BFS just checks whether the neighbor has been explored yet or not. So you can check that by checking if parents of the vertex ID is equal to -1. -1 means that it hasn't been explored. So we apply cond to all of the outgoing neighbors, and we get true for the unexplored vertices and false for the one that has already been touched. The next thing EdgeMap is going to do is it's going to apply the update function to all of the edges that go to one of these vertices marked as true. So this would be all of these green edges I've shown here. And what the update function does for BFS is it just says that atomically mark the neighbor as visited by changing its value from -1 in the parents array to S, where S is the ID of the source vertex. And this compare and swap is going to return true if the update was successful and false otherwise. So it could return false if another vertex came in and did the swap before the vertex you're considering did it. Then the compare and swap would return false for this vertex. But this is going to return true exactly once for each one of these unexplored vertices because one of the vertices is going to succeed in marking that vertex, that neighboring vertex as visited. And then the output of EdgeMap is going to be all of these target vertices of the green edges, such that when we applied the update function to that edge, it returned true. So as I said, it returns true exactly once for each one of these neighbors that we're going to visit. So we mark those as visited and place them in the output of EdgeMap, represented as a vertex subset, and we assign that to the frontier variable, and this is going to be used in the next iteration of BFS. So this procedure just keeps continuing until the frontier becomes empty, at which point we know that we visited all the vertices that are reachable from the source. So that's the pseudocode for BFS and Ligra. The actual code for BFS isn't that much more complicated. Because we're doing this in C++, we have to do memory allocation and freeing ourselves, and then we put the update and con functions inside the struct, which we pass to EdgeMap. Okay, so how do we actually implement this EdgeMap that BFS is repeatedly calling? So let me describe how we would implement it for BFS in particular, and later argue that it generalizes to other graph algorithms as well. Okay, so there are two ways to implement EdgeMap for BFS. The first way is this traditional method of maintaining this frontier of active vertices, and then having all of the vertices visit their outgoing neighbors in parallel and marking the ones that haven't been explored yet as visited. So I'm going to call this the sparse method. So the result of this is that these 4 vertices get marked as visited. They also get a parent pointer because we want to generate the BFS tree. This is the traditional method for doing BFS. Turns out that there's another way to do BFS. This is called the dense method. The idea here is that we look at all of the vertices that haven't been explored yet in the graph, and we loop through their incoming edges one by one. And if we find an incoming neighbor that's on the frontier, then we can just say that that neighbor is its parent, and we can actually stop looping through the rest of the incoming edges if we do find an incoming neighbor that's on the frontier. So in this example, vertices 9 through 12 would find an incoming neighbor on the current frontier. Vertices 13 through 15 end up looping through all the edges, and they don't actually find an incoming neighbor. Okay, so this approach might seem pretty wasteful because you're exploring a large part of the graph and doing a lot of wasted work in terms of edge traversals for these vertices that don't have any incoming neighbors on the frontier. But it turns out that this method actually works pretty well when the frontier is pretty large and many vertices in the graph have already been visited, because in that case, you don't have to look at many vertices, and for the ones that you do look at, it's pretty likely that early on you'll find an incoming neighbor that's on the current frontier, and you can stop looping through the rest of the incoming edges. So notice here that, let's assume that the edges are ordered from top to bottom. Vertex 9 actually found an incoming neighbor on its first edge inspection, and it doesn't even need to look at the rest of the edges. The sparse method, or the traditional method, works better when the frontier is small. And for breadth-first search, Beamer et al. Showed that if you switch between these two methods based on the size of the frontier, you can get some pretty good speedups on real-world graphs. So they did this for breadth-first search. And we asked the question whether this idea of switching between 2 modes of traversal is limited to just breadth-first search, or is it more general? So in fact, this idea is actually more general. You can do it for BFS or BFS-like problems, but you can also do it for other graph algorithms. So what we did was we implemented this idea underneath the EdgeMap abstraction. So instead of having just one version of EdgeMap, we actually have 2 versions of EdgeMap under the hood. We have a sparse version, which is going to take a frontier and loop through the outgoing edges of the frontier vertices and apply some computation. We have a dense version, which loops through all of the incoming edges of unexplored vertices in the graph and breaking out early of this for loop if possible. Of course, the meaning of unexplored and whether breaking out early will depend on the specific application, but the high-level idea of switching between 2 modes of traversal is actually more general than just breadth-first search. So we applied this to a lot of other graph algorithms, and I just want to point out that the decision of which one of these versions of EdgeMap to use is going to be based on the size of your frontier plus the sum of the outgoing degrees. And we have a default threshold that says if you exceed it, then you call the dense version, otherwise you call the sparse version. But if the user actually wants to set his or her own threshold, he or she can also pass this as an optional argument to EdgeMap. If they don't actually care about this, then they don't have to worry about any of this implementation details. They would get the benefit of this hybrid mode of traversal without having to do any work themselves. So here are some numbers showing the different modes of traversal. So these are the 44 running times on the Twitter graph, which is a standard graph used in benchmarking graph systems. It has 1.5 billion edges. So for BFS, we see that, as we expected, we always did the dense thing. It's the slowest among the three. If we always did the sparse, it's faster than always doing the dense mode of traversal. And then finally, we switch between the two. This is indicated by the dark brown bar. Using a default threshold of number of edges over 20, then we get about a 5-fold improvement over the sparse version. We see similar results for some of the other applications. So betweenness centrality, again, dense is the slowest. You get about a factor of 4 by only doing sparse, and if you go to the hybrid, you get about another factor of 2. And connected components, you get a lot just from doing the sparse instead of doing the dense, and you get a little bit more from going to the hybrid, but it turns out that most of the iterations in the hybrid are sparse anyway, so the benefits here aren't that significant. Eccentricity estimation looks like betweenness centrality. All right, so let me now introduce another example in how we show how we implement it in Ligra. So this is PageRank. Many of you have probably seen this before. The high-level idea is that we have PageRank values on the vertices, and we keep applying this PageRank equation to the vertices to update their PageRank values until some convergence criteria is met. So if you haven't seen this equation before, then don't worry about it. Just think of us as repeatedly applying some equation to all of the vertices until some convergence criteria is satisfied. So PageRank is going to use vertex maps. BFS didn't, but PageRank will, so let me now define what the vertex map does. It takes as input a vertex subset, so this vertex subset is the 4 red vertices on the left. It also takes a Boolean function, f, and this Boolean function is going to side effect some data structures associated with the vertices. This is used to update some local information, but it also returns true or false based on some condition. So vertex map is going to apply this function to each one of these vertices in the input. This is also going to return true or false based on the result of the Boolean function. And then the output of vertex map is just going to be the vertices such that when we applied f to that vertex, it returned true. So vertex map, in addition to doing local computation on the vertices, is also sort of acting like a filter to filter out some of the vertices that we might not want to touch in later computations. So I'll show you how we use this in PageRank. So here's a pseudocode. For PageRank, I'm not going to go through all the details. I just want to talk about EdgeMap and Vertex Map. So EdgeMap, the update function is going to say for each vertex, I'm going to pass my PageRank value to all of my neighbors, normalized by my degree. Vertex Map is going to take all these values that I receive from my neighbors for each vertex and do some local computation to figure out my own new PageRank value. In the standard PageRank algorithm, we're always operating on the entire graph on every iteration. That's how the standard PageRank algorithm is defined. And in this example, the EdgeMap and Vertex Map are also going to return the same input frontier. So therefore, we're always going to be in the dense version here, and we don't benefit from this hybrid mode of traversal because we're always operating on the entire graph. So you might wonder whether there's a sparse version of PageRank that could actually take advantage of the changing sparsity of the active set of vertices. Turns out that there's something called PageRank Delta, where the idea is to only update the vertices whose PageRank value has changed by more than some significant fraction from the previous iteration. And this idea was actually discussed before in the Graph Lab paper as well as in a paper by McSherry. So we can implement this in Ligra. So we have to change the update and the compute function. So the update function was the function passed to EdgeMap. So now instead of passing our PageRank value to our neighbors, we're going to pass a change in our PageRank value to our neighbors. The compute function is still going to take all of these changes and do some local computation on it to figure out the vertex's new PageRank value. But it's also going to check this condition, checking if the change in PageRank value for this vertex is greater than some delta fraction. And if so, it returns true. Otherwise, it returns false. And this is important because the output of vertex map is only going to include the vertices such that when we applied the compute function to that vertex, it returned true. So this is basically filtering out all of the vertices whose PageRank didn't change by enough, and therefore in future computations, we don't have to touch it. All right, so here are some performance numbers for Ligra. So first, I'm going to look at breadth first search. So again, this is done on the Twitter graph on 40 cores. So here I'm comparing Ligra with handwritten code for the same application, BFS. And this is actually the code by Beamer et al., which initially introduced the idea of switching between two modes of traversal. And this is actually pretty good code. They submitted this to the Graph 500 benchmark when they published their paper, and they actually got the highest ranking among all of the single shared memory machine solutions. So fortunately, we're able to perform about as well as this handwritten code, but we argue that the Liger code actually requires much less programming effort to write. So I have the number of lines of code here, so this is a proxy for the code complexity, so you can take it for what it's worth. These are only numbers I have, but the BFS code in Liger is about 5 times shorter than the code by Beamer et al., and this is because we have everything underneath the EdgeMap abstraction, whereas the Beamer et al. Code, we have to implement this optimization by hand and also figure out when to switch from one mode to the other and vice versa. Here are some numbers for PageRank. Okay, so in addition to comparing to handwritten code on the same machine, we also looked at all of the high-level graph processing systems that were available at the time we released Ligra, and looked at the one that gave the best absolute performance for this Twitter graph for PageRank, and it turned out that this was GraphLab, so we also compared to that. Okay, so first of all, Ligra takes about 2.3 seconds per iteration of PageRank on this Twitter graph. The handwritten code is faster. It takes about 1.5 seconds, and the reason for this is that there are some additional overheads in Ligra from having to check whether to switch from the sparse to the dense and vice versa, whereas the handwritten code is actually always doing the dense case because this is what you would do in the standard PageRank algorithm. Okay, but still we're within about a factor of 1.5, so that's pretty good. The GraphLab paper, they report a running time of about 3.6 seconds on the same graph. And notice that they're using many more cores here. They're using 64 8-core machines. We also downloaded their code and ran it on our 40-core machine, and it turned out that the performance was a couple times slower here. So we also performed pretty well relative to the best existing system at the time we developed this code. In terms of code complexity or lines of code, it's about the same across the board because PageRank is such a simple application. But if you wanted to implement the sparse version of PageRank that I described a couple slides ago, it would be easy to do this in Ligra. It's also easy to do this in GraphLab. But if you wanted to do this by hand, it would take much more effort because you would have to, again, implement this optimization of switching between two modes of traversal. All right, so the connected components algorithm. Ligra performs almost as well as the handwritten code. GraphLab is a lot worse here, and the main reason for this performance difference is that the connected components algorithm that GraphLab and Ligra use is a frontier-based algorithm. It's processing some subset of the graph on each iteration. Ligra is able to take advantage of the changing density of this active set of vertices, so it's only going to do work proportional to this active set of vertices, whereas GraphLab is actually touching the entire graph on each iteration. So this accounts for most of the performance difference you see here. In terms of code complexity, Ligra and GraphLab are competitive, and the handwritten code is much longer, as you would expect. So across all of the experiments that we did, we found that the performance of Ligra was pretty close to handwritten code for the same applications. We found that it was faster than the existing high-level frameworks at the time we developed this. So our results show that doing graph processing in a single shared memory machine can actually be very efficient. And at the time we developed this, all of the prior high-level frameworks were written in distributed memory. Okay, so one thing is about shared memory graph processing is that it requires the graph to fit on a single machine. Okay, so it fortunately turns out that most real-world graphs can fit on a single machine. So the Twitter graph, it only has 1.5 billion edges, so it can fit in a couple gigabytes of memory. Here are some of the sizes of the larger real-world graphs out there. So there's this Yahoo web graph, 6.6 billion edges. There's this Common Crawl web graph, 128 billion edges. These two are publicly available graphs. And finally, Facebook just recently announced that they have a 1 trillion edge graph, but it's not publicly available. So the first two of these three you can fit on a shared memory machine. So you can get terabyte RAM memory, terabyte RAM machines nowadays. The third one, Facebook, you might not be able to fit if you want to do some more complicated analysis on it, but at least the publicly available ones can fit on a commodity shared memory machine. So if you have access to one of these machines, then that's great. You can do shared memory graph processing and get some significant performance benefits. If you don't have one, well, Amazon just recently announced that they had 2 terabyte machines for rent, so you can also go there and rent one. All right, so now let me briefly describe some ongoing work that I've been doing with some people here at Berkeley. So we've been looking at the graph clustering problem. So the goal here is to find groups of vertices that are well connected internally and poorly connected externally. This is used as a subroutine in community detection where you want to identify groups of people with similar interests or hobbies in social networks. Okay, so it turns out that running standard graph clustering algorithms on very large graphs with billions of vertices and edges can be very expensive because these algorithms require touching the graph many, many times. But fortunately for graph clustering, it turns out that there's this class of algorithms called local graph clustering algorithms that do work proportional to just the size of the graph or just the size of the cluster that they output. So this can lead to significant savings if the output cluster is much smaller than the size of the entire graph. And it turns out that previous studies have shown that good clusters and many real-world networks are actually pretty small relative to the size of the entire graph, and they're localized to some small area in the graph. So actually it turns out that the clusters that these algorithms generate are actually meaningful in many cases. So all of the local algorithms that have been described in the literature for clustering have been described in a sequential setting, and we've been parallelizing some of these local algorithms using the Ligra framework. Some of these algorithms were pretty natural to extend to the parallel setting. Some of the other algorithms required more work to make parallel. At a high level, all of these algorithms are frontier-based, and we're processing small sets of active vertices on each iteration, so it makes them a good fit for the Ligra framework, which has this frontier-based characteristic. And using Ligra is actually crucial to getting this local running time, because Ligra only does work proportional to this active set of vertices on each iteration, whereas some of the existing graph processing frameworks would actually touch the whole graph, and then you would no longer get this local running time, which is crucial to these algorithms. All right, so let me sum up now. So I described Ligra. We have a simple data structure called vertex subset and 2 simple functions, EdgeMap and Vertex Map. I talked about the hybrid traversal optimization. I didn't talk about graph compression. It's another optimization you can ask me about offline. Using these data structures and functions, we're able to express a broad class of graph algorithms. And finally, we found that these codes were simple. They performed pretty well relative to handwritten code and also compared well to existing graph processing systems at the time. And they're also scalable to some of the largest publicly available real-world graphs out there, and you can process these graphs on just a single machine. All right, thank you. And the code for this is all available on GitHub if you're interested in playing around with it.